So now, let me just introduce to you that now we are going to jump into the lattice form. I claim to you that every such system can find a equivalent implementation in the lattice topology. Okay? So the lattice topology, let me just review a little more about the detail. Again, to the far left, we have the input. But then, we will repeatedly, and this input will branch into the bottom line. Okay, it will branch into the bottom line. But then, what comes after this, we will require, let me try to write correctly. We will have the delay, all the delay at the bottom, okay? I'm going to show you like a cascade of the same structure. And so we call this a unit. So for each unit, we have the delay at the bottom. And then we have crossing over, branching to cross over from bottom to top as well as from top to bottom. And again, every time when we see two arrows pointing to flowing into the same node, there is a summation. Okay? Every time when we see two arrows flowing into the same node, there is a summation. So that gives us one unit, one block of the one kind of constituting block, so it's a linear block. Okay? So this is one block, and let me name the branching coefficient. Now we are going to name, actually this structure is going to be symmetric in terms of the branching coefficient. So on top, this branch, this edge, is going to be given a coefficient. Let me just write it down as minus k sub 1, k1, okay? Minus k1. And also the same thing from top to bottom, this is also minus k1. Is that okay? Is that okay so far? That's just a definition. And note that this is the same number. Minus k1, same thing, minus k1. So let's call this. So next I'm going to draw. I'm going to suggest that this is the way we think of it here. Now this is going to be treated as a unit, for some sort, a unit. And then the lattice structure is just simply a repetition of the unit with different coefficients. Okay? So exactly the same connection, same unit. This is, we can consider this as a unit. And we're going to repeat this structure from left to right. We're going to repeat it by n times. And that gives us, that's the definition of the lattice implementation. Okay? So let me just draw maybe one more block. If we are to repeat this structure one more time, so again down here we have another one sample delay, and then on top, at the bottom, at the bottom we have crossing over. We have two branches crossing over from top to bottom and bottom to top. And we are going to call summation here, because two flows are meeting at one node. And not surprisingly, we're going to call these coefficients corresponding to the crossover branches. We're going to call the coefficient minus K2. So that's one repetition of the same structure. One repetition of the same structure. Is that okay so far? And then you can imagine that we are going to repeat this so many times, n times. So the last one is going to be branching over, and we'll call this minus k sub n, the last of such coefficients. And please do not forget that there should be one sample delay right here, right down there, and then you repeat everything. Okay? That's the one final block. And to the far right, so this is what I said. So if we think of this as a constructing unit, Then to the very far right, we have two outputs, right? One input, two outputs. And that's totally fine, whatever. That's the nature of this structure. Okay? One input to the right and two outputs to the far right. But let me just define, actually the top one is what the top one is considered y again, okay? And we want to find a way to determine these coefficients, k1 to km, such that the impulse response is as given. So that becomes let me say that again. Okay, so our task today, so now I've shown you the structure. This is the structure, by definition, the lattice structure. So now the question is, how do we find k1, k2, all the way to km? There are n coefficients. Our task for today is to determine these k coefficients, to determine these coefficients, the k, the k1, k2, the k's, the k coefficients, such that y of z is exactly h of z, x of z, with any given h of z. Or should I say, the task is given h of z, okay? Or say, should I just use the given a0 to am. Given the f by r impulse response, how do we determine this looks a bit strange. Okay. Anyway, so let me just continue. Given the f by r filter, how do we determine the lattice coefficients, okay, such that the overall impulse response is as described by the A coefficients? Okay. Now, given the ladder coefficients, how do we find the lattice coefficients? That's the topic. That's the main topic. Okay, so a bit to proceed on this discussion. It's actually, which one do you think is easier? If we are given the k coefficients, can we determine the impulse response? That's probably easier, right? Let me say that again. If we are given the lattice coefficients, are you confident of calculating the impulse response? And the answer is, I don't know. The answer should be yes. I mean, it's more straightforward. Given the k coefficients, we can find the relationship by backtracking. We probably will be able to figure out a systematic way of calculating the impulse response. That should be doable. Okay? But to proceed with on this, so let me propose. Let's figure out how to calculate A0 to AM given the lattice coefficients. Because it's actually easier. It's actually easier. Okay? It's easier to calculate the ladder coefficient given the lattice coefficients. The other way around is more difficult. It's slightly more difficult. Okay? But so that is to say, we want to we're just given this beautiful lattice structure. How do we calculate the impulse response? All right? The very far right is out, very far left input. Okay? So, but let's define a few notations. All right? Any questions so far? Any questions so far? Do we know what we're going to do? Okay? We all know what we're going to do next. Any questions? Let me define a few notations. All right? So now I'm going to refer. It's could be a little confusing because we are going to use the letter A, but that letter A has nothing to do with letter A here. And I'll show you in a moment. So assume that on the top lane, I'm going to refer to this as the top lane. This at the bottom lane. Lane is so down, lane. Okay. I'm going to call this the top lane. You can, from time to time, I'm going to try to invite you to think of this as if you are driving a car, riding a motorcycle or whatever. You're two-lane tracks, and you can switch from one lane to the other lane, and vice versa. Okay, so I'm going to call this top lane and bottom lane. And I'm going to name the variables. I'm going to name the top lane variables using letter A, the bottom lane using letter B. I say this is a bit confusing because please do not confuse the A that I'm going to draw there with the A coefficient I wrote down right here. Okay, so a bit of a definition. I'm going to call this place A, no, this. Now A and B are signals, okay? I'm going to call the top part here, there is a superscript A0 of n. So that's the right here. I'm going to call it right here as B0 of n. B superscript 0 of n. So next, before entering the second block, let me just explicitly draw the block. Okay, this is another block, the second block. This is the second block. And so immediately after the first block, we have two outputs, right? So on top, I'm going to call it A superscript A1 of n. At the bottom, similarly, I'm going to call it B superscript 1 of n. Okay, right immediately after the first block. And you probably can imagine that similarly, I'm going to call whatever right here as immediately after the second unit, the second block, I'm going to call it on top A superscript 2 of n. And at the bottom, I'm going to call it similarly B superscript 2 of n. So you see that B, the superscript, refers to how many blocks afterward. Okay? B superscript 0 of n, B superscript 1 of n, B superscript 2 of n. Alright, is that okay? So naturally, according to this wave notation, this notation y of n will be defined as written as A superscript n of n, which means that it is the top lane signal immediately after the m, the very last block. And actually the bottom lane here we still have, that's the output, and it can be written as B superscript n of n. So these are just some signals. Imagine that if you have some kind of probe, you can measure the signal anywhere you want. So that's the meaning. Okay. Imagine that you can measure the signal at any place you want. Okay. So these are the notation where we give to the signal you can measure anywhere in the network. All right? Okay, so now come back to this question. How do we calculate the impulse response? Basically, this is the impulse response. Okay? How do you calculate, or should I say this is just H0, H of 1, H of n, H of n. So that's the impulse response. How do we calculate the impulse response of this network given the lattice coefficients? And first of all, let's answer a few just by inspection. Let's observe this in the work, and I'll ask you a few questions. is this system FIR or IIR? It should be an FIR because there's no feedback. Note that even though we have crossovers, the flow is entirely from left to right. So this is an FIR system. There's no feedback. Okay? And secondly, if it is an FIR filter, how long is the impulse response? How long is the impulse response? So that is at most how many delays can we have in this network? Okay? And the answer should be clear. The answer is at most we can have. So this is why I want to imagine this as like two-lane traffic. And there are so many different paths. In fact, there are 2 to the nth power total possible paths. If you will. You imagine this is you're sending the input from the left, feeding it to the network, and the current or the traffic can go any possibilities along the network from left to right. So we agree that they are, because since there are 2n chances to switch lanes, so there should be a total 2 to the nth power possible path. If you want to, 2 to the nth different ways to travel from far left to the far right. Can you agree on that? Okay. So that's the observation. First of all, definitely is an FIR because there's no feedback. And secondly, the longest delay in this network from left to right is n. And that corresponds to the longest delay corresponds to which path? It corresponds to first coming down from top to bottom. And they keep all the way at the bottom until the very final while we switch over to top. So these things I need to repeatedly go back to this graph. So the longest delay corresponds to this path, this very path. It's all the way keeping at the bottom lane, all the way until the very final, and including this final and the inverse, and then in the end, feeding to the output. That's the longest delay path. The path is the longest delay. All other paths have a shorter delay. That is to say, any other possible path has a shorter delay, depending on how many blocks we are staying on top. Because the top lane does not have the one sample delay, does not have the inverse, right? And we all see that the top lane does not have the inverse. All the inverse blocks are at bottom lane. So this path is the path with the longest delay. Okay? So that's two observations. Now, which path has the shortest delay? The shortest delay is all the way stay on top, right? So this thing here has the shortest delay. It should be pretty clear. All right, and no other path has no delay. This is the only path which has no delay, because once you switch to the bottom, you have to delay by a few samples until you switch back to the top. Okay, so this is the only path that does not have any delay. Therefore, by this observation, the shortest delay is 0. Okay. So from the observation, immediately we can solve two of them. Okay, given the lattice coefficients, immediately we can solve the sample with no delay, the coefficient with no delay, and the coefficient with the longest delay. That's kind of immediately know. Okay, so immediately have the conclusion. The sample with the shorting delay h of 0 is 1. Because here we don't have any more multiplication, at least for the way this is defined here. Okay? So the way this is defined here, h of 0 is the path, corresponds to the path, the only path, one of the only paths which has no delay. And that path has a gain of 1. That path has a gain of 1. Whereas the longest delay, what's the associated sample value? What's the corresponding sample value? This path. Okay, so we all look at it here. So for this longest delay path, it goes down here, and there's a Z inverse, and then there's another Z inverse, and another, and another, and another. So there are a total of M Z inverse before it finally switches back to the top lane. And here we have a coefficient minus Kn. Okay, so immediately we can reach a conclusion that the last sample should be minus Kn. So that's kind of a simple observation of thinking. Okay. Now I invite you to think of this network as it has two lanes, and you can switch from top to bottom, from bottom back to top at n different places. Right here, right here, right, and so on. Right? But now, immediately you probably now start wondering, how do we calculate H1, H2, H3? Any idea how do we calculate H1? Please discuss this later. For 1 minute. How do we calculate H1? How do we calculate H1? How do we calculate H1? So you see things are getting complicated. Any suggestion? How do we calculate H1? It's possible you can just, basically you need to find out all possible paths with exactly one sample delay. And each path is going to be associated with a gain. And then you just basically sum up all the gains of all the paths that have exactly one sample delay. Okay, so is that making sense? Making sense so far? So it's doable. So otherwise, based on these observations, to calculate H of 1, I suggest first find out all possible paths with exactly one sample delay. And secondly, for each of path, there should be an associated path gain, okay? The gain of that path. Each of such paths. And 3, summing over all possible paths. Okay, roughly speaking, it's doable, but it's not going to be a very, so that's only for H1. How about H of 2? Things are becoming a mess. So you need to find out all the possible paths that has exactly 2 samples. The things are getting more complicated, right? But it seems that, I'm just trying to suggest that it seems that yes, indeed, it's possible to use combinatorics. It's possible to use combinatorics, NGS, N factorial, K factorial, such things to express, to figure out a general expression for H1, H2, H3 in terms of the lattice coefficient. But it's going to be a mess. I hope you agree with me. At least you're a super genius of some sort. You can just tell me what the general expression is. It's going to be a mess. And the general expression is not going to be so clean. Okay, so next I'm going to suggest that just forget about, let's just forget about general expression, but instead we want to find kind of a systematic approach to propagate from one unit to the next unit, and from the next unit to the second next unit. So you can figure out a systematic way to propagate the coefficients from left to right and we solve the problem. And all we need is an algorithm. Okay? So my conclusion is that you want to solve this by combinatoric, the comments or remarks. If by combinatorics, 它列组的和弦 combinatorics is going to be a mess. For example, no example, a mess. So let me suggest. So my suggestion explains why these notation comes in handy, conveniently. Okay? So assume that just using our usual notation, with every signal in time domain, the corresponding uppercase would be the Z notation. Okay? The corresponding uppercase 大写的 capital B is the corresponding Z notation of the signal in the Z domain, and so on and so forth. So A superscript 2 of Z 大写的 A capital A and 大写的 B capital B superscript 2 of Z. Alright, so in the next I'm going to suggest let's try to figure out A1, B1 in terms of A0, B0. And let's figure out A2, B2 in terms of A1, B1. And in general, we can figure out A superscript J plus 1 and B superscript J plus 1 in terms of A superscript J and B superscript J. Is that clear? And that's actually very straightforward. So systematically, when we propagate from left to right, in the end, we can calculate A superscript n and B superscript n if we are given the input. Okay, so what we're going to show next, we are not going to see a general expression of the impulse response in terms of the lattice coefficient, but instead we find an algorithm. Okay. So the suggestion is that by recursion, so let's just draw one unit right here, okay? If on the left, now suppose that we are immediately after the I minus 1 unit. So the input to the left on top is A superscript I minus 1. And then after 2 crossing over, and the crossover coefficients are, by definition, minus K sub I minus K sub I. And there is actually a Z inverse right here. Okay, so if to the top left of this unit, we have A and B, denoting the top and bottom respectively. Immediately after the I minus I, after so many units. And this is one more unit to consider. So one more unit, and now to the output, suppose that just by definition we have this notation. So to the right, now we go across one more unit. Therefore, the output on top and the bottom is going to be written as A superscript I and B superscript I, respectively. Superscript, subscript, no. Some delta, shall delta, superscript, subscript. Right? So now this should be not so bad. I mean, so the question now reduces to how do we express AI and BI in terms of A minus I minus 1 and B I minus 1, given with one more coefficient. This should be very, very straightforward, right? This should be very straightforward. So let's just work it out together. Okay? Let's just work this out together. So A superscript I of Z, that's on the far right here. It should be the sum of this and this, right? So it should be the summation of one path is directly feeding from left to right. That term is still there. Plus this path. This path. And that path should be plus B. That's the input right here. Okay? Times Z inverse times minus Ki. Or just a bit of bookkeeping. So that is A superscript I minus 1 minus K sub I Z inverse B, that input at the bottom from the left. That okay? Very straightforward. Very straightforward. Not hard at all. And similarly, since we are going to establish a recursive relation, we also need to figure out how to express the bottom output Bi in terms of combination of the input. Okay? So let's do the exact same exercise. Now, we also have two paths. One is this path, the other is directly staying at the bottom. Two paths. So I hope it should be clear that now the bottom path is minus Ki times A top that's that path. And one more path is staying at the bottom, that is B of superscript I minus this thing times Z inverse. So that's an important recursion relation that shows us how to propagate from left to right by 1 unit. How to propagate our answer across 1 unit. Okay? So if we can do this, we can just repeatedly doing it. And then propagate from the far left, where A and B both equal to X. A0 and B0 are just X. Okay? So now, we're going to suggest an algorithm. I'm going to suggest an algorithm 1, which is not our final algorithm yet, but I'm going to, based on this very simple idea, propagation from left to right. I'm going to suggest first, note that A0 of Z and B0 of Z are actually exactly the input. Exactly the input. Okay? And since we want to calculate the impulse response, let's say x of Z is 1, which means that x of t is x of n is delta function. If we are interested in feeding the impulse to the system, and now we know that at that moment when we feed the input to the system, x of Z consists of one sample. Okay? To the far left. Now, if we consider x of n to be the delta function itself, then we can try to propagate 1 unit after 1 unit, and in the end calculate the impulse response. Okay? So suppose that A0 and B0 are both initiated with 1 in the z domain, which corresponds to the delta function in the time domain. And then for I equals to 1 to n, do this. If this is a recursive relation, let's give it a name. Do a recursion equation 1a and equation 1b. Okay? So for I, how many we use Python? I'm now considering how should I indent by 110? Okay, maybe indent by 110. Okay. For I from 1 to n, just do equation 1a and equation 1b. And then we're done. And in the end, now let me just explicitly put an n here. I mean, matter I think the accompany with your or n. And 3 is return. Return a n. Alright, so that's kind of pseudo code. Very convenient. The idea is very simple, really very simple. Just repeat this option, this action. Repeat this action at the same time. Like we're done. Alright, so but surprisingly, any questions so far? Any comments so far? So far, it should be actually not that bad. I mean, this should be pretty straightforward. But surprisingly, in this network, if the input is an impulse, is a unit impulse, if the input is delta function, it turns out that top lane, if you just observe the top lane and the bottom lane, okay, let's say at the second place, for example. This is interesting. This could be interesting. If you just see the impulse to the left as an input, then exactly at any moment, at the output of any unit, if you just compare the top lane signal and the bottom lane signal, to make a comparison, it turns out there is a symmetry. Turns out the bottom one will be the bottom signal will be the top signal exactly in reverse, and that could be quite surprising. Let me say that again. If you just put impulse here, and then of course if you wait for long enough, it will propagate